Part 3, this is for questions 21 to 30. Question 21, X, Y, and Z are elements in period 3 of the periodic table. The results of some experiments carried out with compounds of these elements are shown. Now here we are having X. They are saying result of adding the oxide of the element to water, no reaction. So in period 3, oxides of these elements, when we add them to water and we see no reaction, we have gotten aluminium and silicon. So these two, they don't hydrolyze in water and they are not soluble. Okay, that is silicon and aluminium, no reaction. Result of adding the chloride of the element in water hydrolyzes. So again, it can be silicon and aluminium. These ones hydrolyze. Then result of adding the oxide of the element to HCl forms a salt. Yes, aluminium oxide is amphoteric. It can react with the acid and then with the base. Okay, so you can put there aluminium. Then Y forms a hydroxide. Now, when we look at X here, let's go to the options. Which statement is correct? X is aluminium, X is silicon. And element Y is magnesium, element Y is sodium. Let's look at Y. Oxide of Y, when you put it in water, it forms a hydroxide. When you get magnesium, and if we say magnesium here, oxide, then plus water, indeed we shall get magnesium hydroxide. Then the same to sodium. When we add water, we shall get sodium hydroxide. Okay, sodium hydroxide. And we need to put a 2 there. Then they're saying result of adding the chloride of the element to water. This one dissolves. Yeah, these ones, when we add the chloride to water, indeed they dissolve. Sodium chloride, you put it in water, it just dissolves, the same as for magnesium chloride. That is true. Then forms a chloride salt. When you get the magnesium, when you get the oxide and then you react it with the HCl, these ones are basic oxides, so they can react with the oxide. Okay, so these two indeed can do that. So any of them, okay, any of them can be. So it can either be magnesium or sodium. But then when you look at option A, when you look at X, is it silicon or aluminium? Based on what I had here, okay, here, aluminium chloride, aluminium oxide can react with HCl to form the salt here, the aluminium chloride. Okay, so that means our options here, from the options we are going to pick what? A, because in A the X has to be aluminium, it satisfies all of these ones here. Okay, here silicon fails, you see that? So I don't need to look at any other option here. Our answer has to be this A here. But then when you look at these ones here, if you say Z is element P, they said Z forms an acid. The oxide of Z, if it is the oxide of phosphorus, you put it in water, indeed you form an acid. That one is okay. Then result of adding the chloride, it hydrolyzes. That one is also okay. Or we get HCl even produced from there. And then result of adding the HCl, okay, to acid, and then it hydrolyzes. No, that one is wrong. So Z then cannot be P. Of course, Z cannot be aluminium. So our answer is that A. Question 22. The flow diagram shows two successive reactions starting from the element Q. Element Q is calcium or barium. So first they are saying you heat it with oxygen, we get an oxide, not so. So we can have barium. It is either barium or calcium. So suppose I take it to be calcium, then plus the oxygen, we are going to get calcium what? Oxide. Okay, I can put a half here. Then from here, if we add water, we get a hydroxide. This one is going to be calcium what? Hydroxide. The same thing with barium. Okay, so barium plus a half of oxygen, this one will give us barium oxide. Then also when we add water, this one will give us barium hydroxide. And we know in group 2, the hydroxides of these group 2 elements increases down the group. So barium hydroxide is much more soluble compared to calcium hydroxide. Now they are saying element Q forms a nitrate that is less thermally stable than strontium nitrate. Now we know that in group 2, as you go down the group, okay, the nitrates or carbonates of these group 2 elements, their thermostability increases down the group. Okay, thermostability of group 2 nitrates or carbonates increases down the group. So that means if element Q forms a nitrate that is less thermally stable than strontium nitrate, then Q has to be above strontium nitrate. So if I take magnesium here, then I have calcium, then we have strontium, barium is below. You see that? So this barium here is if I can put on the nitrate. So the most thermally stable one is barium nitrate. To be thermally stable, that means it requires a lot of heat to break that compound. Okay, so it will take much more heat to break this one here. The explanation we give it in A-level content, that is chapter 19, okay, of lattice energy, where we talk about the ion polarization. Now the element Q has to be higher than strontium, okay, and the one that is higher than strontium is what? Calcium. You see that? Is calcium. So by the way, compound R can be this one here, or this one here. You see, because after adding water, then we get compound what? R. So they said, what is the identity of compound R? It has to be calcium what? Hydroxide. We are choosing from here because Q forms a nitrate that is less thermally stable. Calcium nitrate is less thermally stable compared to barium nitrate. So therefore R has to be calcium what? Hydroxide. Question 23. Which anions are formed when chlorine is passed into cold aqueous potassium hydroxide? So cold aqueous potassium hydroxide, we also have chlorine reacting with hot, okay, concentrated potassium hydroxide. Okay, this one is a strong alkali. You get it? So what we have in the books is sodium what? Hydroxide. So potassium hydroxide and sodium hydroxide, they work the same way. So if I put potassium hydroxide here, then I react it with chlorine. This is a disproportionation reaction. So for cold, first of all, you get sodium chloride. Okay. Then there is also what? Water. So whether it is hot or whether it is hot and concentrated, or it is cold and aqueous, you are going to get sodium chloride and water. Okay, then here when it is cold, we get sodium chlorate 1, this one here. So the ion here is that, you see, and then the chloride. These are the ones you're seeing here. So that means our answer is what? Is A. Maybe to balance this one here, what do we do? By the way, I'm supposed to put here potassium chlorate 1 and potassium chloride. Okay, just like we do for sodium. Pardon me there. If I'm to balance, I think we shall put a 2 here because potassium is 2 and then oxygen is 2 now, oxygen is 2, then hydrogen is 2, hydrogen is 2, and then chlorine is 2, chlorine is 2. So that's how we balance it. Then question 24, what increases for each successive element in period 3 from sodium to sulfur? So we have the highest oxidation number of element seen in an oxide. Yeah, we actually see the oxidation numbers increasing because of the increase in the valence shell electrons, the electrons in the outermost shell. So this one is actually correct. Then the melting point of elements. No, the melting points of elements, we can have sodium here, high melting point, so it increases. When we go to magnesium, then aluminium, it also increases. Then for silicon, it shoots so high, okay, because it has a giant covalent structure. Then from silicon, we go to phosphorus, and for phosphorus, it has to go down because this is simple molecular. These ones are, they have giant metallic structures. So this is phosphorus, and then we get sulfur. It also has a simple molecular structure, but we have S8, and then this one is P4 for phosphorus. Now you see that here there are more covalent bonds compared to this one here, so that is why the melting point here is slightly higher. Remember, when we are talking about the melting point, we look at structure and bonding, then also the strength of the intermolecular forces, the strength of the forces between these atoms also. Okay, now next we are going to have chlorine. Chlorine is simple molecule, it is even a gas, and these ones are solids at room temperature, so its melting point has to surely be below these ones here. And then we have argon also down there, because for argon we are having a gaseous atom. Okay, it is also a gas, so that is what we are having. It increases, then it decreases, so this one has to be off. Then option C, the number of occupied orbitals in the orbital. This one is not also correct because we are putting these electrons in the same shell, in same principal quantum number. Okay, 3. So we're having the 3s and the 3p. We are putting only in these ones here, so we are not increasing the number of shells that we are adding there. There is also 3d, by the way. You see that? So this one is also off. Then D here, the pH of the solutions of the chlorides in water. pH doesn't increase because as we go across the period, the chlorides here, when we put them in water, look at something like silicon. For chloride, when you add it to water, you are going to get silicon dioxide, then plus the HCl. You see that? So this HCl you're getting here, you're going to have, this one is an acid, you see? So the pH has to be increasing. So I mean has to be reducing because of the acid that is produced here. So this one's hydrolyzed. So therefore, our answer has to be A. I repeat, the oxidation numbers here keep on increasing. Why? You have for sodium oxide, the oxidation number of sodium is a +1. Magnesium oxide, the oxidation number is a +2. Aluminium oxide, the oxidation number for aluminium is a +3. You see they are increasing. Then for silicon 4 oxide, that will be a +4. Then for phosphorus, here pentaoxide, this is a +5, so it keeps on increasing. You see that? And they said up to sulfur. So we can have sulfur trioxide, by the way. We can have sulfur dioxide. So we have seen the trend. It is increasing. That means our answer has to be that A. Okay. Then question 25. Which statement about an ammonium ion is correct? Now, an ammonium ion. Let me rub off this one here. We are already done with it. In an ammonium ion, we have dative bonding in there, hydrogen, then hydrogen here, here, and here. It is a tetrahedral structure, 109.5, that is the bond angle. And then we also have, this is actually an ammonium ion that donates, so the nitrogen in here donates the 2 electrons to the proton here. We call it a proton because if hydrogen has 1 electron in the outermost shell and then 1 proton here in the nucleus, when it loses the electron, then we get the nucleus. So it is remaining with only the proton in the nucleus. So that's why we call hydrogen ions protons. You see that? Now, first of all, this one is trigonal pyramidal. So for it is like this. Using valence shell electron pair repulsion theory, so we have a lone pair of electrons here. So the repulsion between the lone pair and bond pair is stronger than the bond pair. Okay? So this one here, that is here, the bond pair, if it is replaced with the lone pair, then there is going to be stronger repulsion here. So this angle here that we get in between these ones here, the bond pairs, it is going to be smaller than this because of the more repulsion, stronger repulsion from here. You get it? So this angle here is below 109.5, which can be 107. The moment you remove this and you put a bond angle, then they expand, okay? Because the match resistance that is from here has been reduced. So then it comes to this kind of what? Shape. So the shape now changes from trigonal pyramidal to tetrahedral. You see that? Yeah. Now they are saying all the hydrogen-nitrogen bond angles in the ion are 90. That one is off. The angles are 109.5. Then all of the hydrogen-nitrogen bond angles in the ion are 107. Even this one is wrong. This is the angle. It is 107 if it is in ammonia where we are having trigonal pyramidal. You see that? Okay. Then next, the ion contains the NH dative covalent bond, which is weaker than the other 3 NH covalent bonds. First of all, the ion contains this N to H dative covalent bond. This one, I talked about it. But it is not weaker than any other. All of these ones are bond pairs. 2 electrons shared. That is all. So just because this one is a dative bond, it doesn't mean that it is stronger or weaker than these other ones. They are all covalent bonds. You see that? So this simply implies that this one is off, and therefore our answer has to be D, where they are saying the ion will react with the base as it is a weak acid. Indeed, if you actually get any ammonium salt and you warm it with a strong alkali, ammonia is going to be given off. So when I react this one with a strong alkali, like this, we are going to get off the ammonia, then plus water. Okay, so this one here has lost a proton. So it's a proton donor. And a proton donor is going to do what? A proton donor is going to form, a proton donor is going to donate a proton. So that is an acid. You see that? I can even change this one actually to something like this. Or I can say ammonium hydroxide. That is what I get from here. When these two react, we get ammonium what? Hydroxide. And ammonium hydroxide is a weak base. You see? So that is that. Question 26. An alcohol U is reacted with hot acidified potassium dichromate solution. That means we are going to have an oxidation here. The organic product of the reaction contains 58.8% carbon, 9.8% hydrogen, and 31.4% oxygen by mass. What is the identity of the alcohol? Now, when you look at what we are having here, if this is an alcohol, it is being oxidized by potassium dichromate. That means this alcohol can be primary or secondary. Okay, this one is a primary alcohol. How about this one here? Let's check. This is CH3, then C, there is an OH here, then there is 3-methyl. Okay, so I can have the methyl group here, 1 2 3, then 4 here. I think that is the one. 3-methyl, you turn to O. Yes. So this one, when we oxidize, it is a secondary alcohol, so we can get a ketone. You see that? Then this one here, 2-methyl. Now this one is going to be CH3. Then we shall have the CH3 here, then the OH. Then you will have CH2, CH3. 2-methyl, 2-butanol. 2-methyl, butan 2O. This is the one here. This is a tertiary alcohol. It cannot be oxidized. So this one has to be off right away. Okay. So these three are going to be oxidized. Now let's check which one is it. So we have, let us first find the empirical formula of the organic product. So we have hydrogen, then we have carbon, and then oxygen. So percentage mass is 58.8. I will divide this one by 12 to get the moles. Okay. Then hydrogen 9.8 divided by its AR, which is 1. Oxygen is 31.4 divided by the AR, which is 16. What do we get here, here, and here? Then after we get the mole ratio, 58.8 divided by 12. This one gives us 4.9. Then here 9.8. Then how about here? 31.4. Then divide by 16. This one is 1.9625. 9625. Then we can now find the mole ratio. So we divide all through by the smallest, which is 9625. Also here we do the same. Definitely here it also has to be the same. So here we get 1. How about here? 9.8 divided by 1.9625. So there we are getting 4.99. That is like 5. Okay. How about here? I'll just come back to this one here and I change this one to 4.9. So this one is 2.5. Okay. If this one is 2.5, remember empirical formula is the simplest whole number ratio for the number of atoms that are present in a compound. You see that? So the empirical formula here is going to be, get these, we shall multiply them by what? By 2 to get the whole numbers, because you are not going to have 2.5. We said simplest whole number ratio. This one is not a whole number. This one is, this one is. So we multiply through by a value that is going to make them what? Whole numbers. So that means carbon here will be 5. Then hydrogen here will be 10. And then oxygen here will be 2. And remember, the empirical formula can be equal to the molecular formula. Okay? Now, if the empirical formula is equal to the molecular formula in this case, and we're having 2 oxygen atoms, this one is going to be a carboxylic acid. Are we there? Because it has 2 O's. Remember, we are oxidizing an alcohol. So we either get a ketone or a carboxylic what? Acid. And this one here is giving us a ketone. These 2 can give us the carboxylic acid. Are we there? Now, since these 2 can give us the carboxylic acid, this one I'm already putting it off because it is going to give us a ketone which has only 1 oxygen. Are we there? But yet here we are having 2. Now, how many carbon atoms? We are seeing these ones are 5, but propan 1O has 1. You see that? So that simply implies that our answer is going to be C here, where we are having the 5 what? Carbon atoms. And propan 1O, this one is CH3, CH2, 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 then CH2OH. When you oxidize this one here, you're going to get a carbox. First, you'll get an aldehyde, pentanal, that is CH3CH2, then CH2CH2, then we are supposed to have CHO, but then further oxidation is going to take place, and then we get a carboxylic acid, which is COOH. If we try to count the carbon atoms, 1, 2, 3, 4, 5, that one is okay. Then hydrogens, 3, 5, 7, 9, 10. This one is also okay. How many oxygens do we see? 2. So don't you think the answer is that C pentan 1O? Question 27. Which row shows a primary, secondary, and tertiary alcohol? A primary alcohol, you look at this carbon atom holding the OH, it must have 2 hydrogens. Okay, in fact, let me write it like this. Put the OH here. It must have 2 hydrogens and 1 alkyl group. A secondary alcohol must have 1 hydrogen, okay, and then 2 alkyl groups. They can be the same or different. You see that? So this carbon holding the OH must have these 2 alkyl groups and 1 hydrogen atom directly attached to it. And then the tertiary must have 3 alkyl groups that are all different. No, not necessarily different, but 3 alkyl groups, and it has no what? Hydrogen. That carbon there has no hydrogen, which is holding the what? The OH. All right, now when we look through, I will come to this one here. Look at this D here. I'm seeing 1 alkyl group, the methyl, 2 hydrogens. So this is a primary alcohol right here, based on what I said here. Then secondary, go to this one here. It has 2 alkyl groups. I said the alkyl groups can be the same or different. So these are 2, then 1 hydrogen here. 2 alkyl groups, 1 hydrogen. So what does this mean? This one is a secondary alcohol. Go to tertiary. The 3 alkyl groups are all the same. They can be the same or different. And there is no hydrogen attached to this carbon, which is holding the OH. So this one is a tertiary alcohol. So our answer is D. The rest, they fail. Okay. 1, look at A. This one is a primary alcohol. Okay, we agree. This one here has a primary alcohol end and also the secondary, you see. Now, because of this being primary, then this one fails. You see that? And this one here, of course, it is not tertiary. There is primary here, there is secondary here, there is primary here. You see that? Then come to B here. It has primary here. You see? So now they actually projected all of these somehow to confuse you. You have to look at that carbon holding the OH. This carbon here is just holding the hydrogen and these other groups here. You see that? You look at the carbon holding the OH and then the groups that are attached to it. When you come to this one here, this one is actually tertiary, and yet they are saying secondary. So this one is already off. When you come to this one here, it is primary, yes. But then when you come to this one here, there is primary, and also this one is primary. So it fails. The whole thing fails. That's why our answer is what? D. Question 28. 1-chloro-2-methyl-butane reacts with sodium cyanide in a nucleophilic substitution reaction. Now, nucleophilic substitution reaction, we have 2. We have SN1 and then also SN what? SN2. Now, for SN1, we have 1 species which is involved in the rate determining step, and that is for tertiary halogenoalkanes. Okay, then for SN2, even by the way, secondary can undergo this because of the more alkyl groups that can be in position to stabilize the carbocation. And then for SN2, this one is for primary what? Carbocations or primary halogenoalkanes. Now, in here, is this primary or secondary? So let's check. Butane is 1, 2, 3, 4. 1 chloro. So let's put the chlorine here on the first one. 1 chloro, then 2 methyl. Methyl is here. Then what else is remaining? So we have to put this one here, and then CH, then CH2, CH3. This is how it looks like. Now from here, this one is a primary halogenoalkane. So meaning that this one will undergo SN2. So chlorine, we know it is more electronegative compared to carbon, so it will tend to pull bonding electrons towards itself. Okay, and then in doing so, it attains a partial negative charge, and then carbon will attain a partial positive charge. You see that? Now this one has only one group here. This one, we take it as one alkyl group, so it has a positive inductive effect towards this. So it is the only one that is stabilizing the what? This carbocation that can result from here. So therefore, this one is weak. It cannot cause this one like to go away right away. So in that sense, we are going to have what we call SN2. So we shall need a nucleophile. Now this is the cyanide. This nucleophile will have to bring in electrons. Okay, if it brings in the electrons, then this bond can be in position to be broken. You see that? But what happens, we always do this, and then this one goes off, then we write the what? The product. But what happens is that we leave this bond here, then there is a hydrogen here, there is a hydrogen here, then there is a new bond here being formed. That is for the cyanide. Okay, now this bond that is going to be broken here for chlorine, we also make it what? Dotted. You see that? Then let's write this other one here, this other group, CH2, then CH3. So this is an intermediate from there. And then what happens is that now this one will get off, because now look at carbon. It has how many bonds? 1, 2, 3, 4, 5, and it is supposed to have 4. So this one now breaks off, and then you will have the CN, then CH2, CH, then CH3 in brackets, then CH2, CH3. You see? So this intermediate here, let us see. Of course, this one is a fast reaction. This one is slow. This is the rate determining step. Then this one is going to become fast because carbon here is so unstable. This compound here is so unstable. Carbon cannot have what? 4 bonds. So that one is very fast. And then when you look at our options here, the answer has to be what? A. You can see these ones dotted, and carbon has how many? 5 bonds in there. So that is that here they are giving you something wrong, because look at the structure they have given you. This is 2 chloro, 2 methyl. You see that? This one here, the chlorine and the methyl, they are on this second carbon. And yet they said 1 chloro, 2 methyl. You see that? The rest I'm not going to look at them. Everything is just wrong. So our answer here has to be what? A. Question 29. When 0.010 moles of hydrocarbon X reacts with 720 cubic centimeters of hydrogen at room conditions, an alkene is formed. Now, to form an alkene, that means we are having an alkene. Okay? We have alkene plus hydrogen. Then you get, of course, here under nickel as a catalyst. Then you'll get an alkane. Okay? This one is unsaturated, then this one becomes saturated. Now, let us see the moles of hydrogen. This one was done under room conditions. 1 mole of a gas at room temperature and pressure occupies 240 cubic centimeters, right? So that means the moles of hydrogen here, we are going to have 720, then divide by the 2000, 24,000, okay? Then what do we get here? 720, we divide by 24000. This one gives us 0.03, 0.03 moles. For this kind of reaction, a double bond in an alkene, okay? A double bond reacts with 1 mole of hydrogen to give you this saturated compound here, okay? So I don't know whatever is here or here, but when you put the hydrogen, it becomes saturated, so it is 1 mole. Now this is 0.03. Now we have for the hydrocarbon X and then the hydrogen here. So this one is 0.01 and this one is 0.03. Let's get the mole ratio. So mole ratio is going to be, you divide all through by the smaller one, this one here, and then this one here. Automatically this one will be 1, this is 3. So this simply implies that we are having 3 moles of hydrogen that are used here for 1 mole of X. You see that? So that means there are 3 double bonds, 3 carbon to carbon double bonds, okay, in X. Because each of them, like I said, reacts with 1 mole of hydrogen. And we are seeing here how many? 3 moles of hydrogen. So when I look at all of these, where do we see the 3 carbon to carbon double bonds? These are how many? 1, 2, 3, 4, 5, 6. This one has to be off. We are looking for 3 off. Then here 1, 2, 3, 4. Even that one is what? Off. We go to C, 1, 2, 3. Yeah, this one is okay. We come to this one, 1, 2. This one is off. So that means our answer is what? C. Question 30. An alkene reacts with hot concentrated acidified potassium permanganate to produce a single organic product as shown. Now, with hot concentrated acidified potassium permanganate, the double bond is actually completely broken in an alkene. So we are going to see this one broken, this one broken, this one broken, this one broken, and then these carbons here in the in these double bonds are oxidized. Okay. Now we can get carboxylic acids. We can get what else? We can also get ketones there. Now, when you look at this product here, how many carbon atoms does it have? 1, 2, 3, 4, 5, 6, 7. Okay, there are 7. So let's count here. What do we have? The carbon atoms we have in these options given: 1, 2, 3, 4, 5, 6, 7, 8. So this one is off. Okay, this one is off here. Why is it off? Because when we break here and we oxidize, you are not going to have a carbon dioxide coming off. The carbon dioxide will only come off when you have a CH2. Okay, when you break here and then you oxidize this one here, this one will come off as carbon dioxide. In fact, it will be methanoic acid, then which breaks down to carbon dioxide and water. You see? But there is nowhere we are going to get, because these ones are rings, you see? So this one with carbon atoms that are more than what? 6, we are going to take it off. So A has to be off. How about this? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay. These carbons here have to be 7. And here we have seen 1, 2, 3, 4, 5, 6, 7, 8. So this one goes off. And also B here. 1, 2, 3, 4, 5, 6, 7, 8. So this one also goes off. So that means we can now look at C and D. So this one is off, this one is off. Let's come to this one here. How many? 1, 2, 3, 4, 5, 6. 7. Okay. And here we are also having 7 carbon atoms. Are we there? Then how about D? 1, 2, 3, 4, 5, 6, 7. Perfect. Now let us compare these two when we oxidize. So break here, and you also break here. So that means here I'll have this carbon here. It has a hydrogen. That means this one will go to a carboxylic acid. Okay. So we shall have a carboxylic acid. I can put OH here, and then O there. Then after that, there is of course this one here. There is this. There is that. There is this. Now there is a carbon here. There is a methyl group there. That means here we shall get a ketone. You see that? This one will be a ketone. And we are seeing a ketone then with a methyl group, which is here. Then there is this. But here we must be having what? A methyl here, which is here, but it is not there. You see? That means this one here is wrong. The answer then has to be D. But let's check D here. We are going to have a carboxylic acid here, then with the OH, just like here. Then when it comes down here, we shall have this, then there is this, and then you come to this one here. Now this one will give us a ketone here. So we have the methyl group, and then that. Now you can see that where there is the CH3, and then this carbonyl. So there is CH3, then the carbonyl. Are we following? Next. Then we continue to a carbon here, then the methyl group. So continue to the carbon and then the methyl group, you see. Then continue to this one here, which is this one here, which is this one, then here, which is this one here, then carboxylic, that is carboxylic. So you see that our answer is actually a D.